Here's Rust in Production, a podcast about companies who use Rust to shape the future of infrastructure. My name is Matthias Endler from Corrode, and today we talk to Jeff Kao from Radar about building a high-performance geocoding platform with Rust. Jeffrey, thanks a lot for taking the time today for the interview. Can you say a few words about yourself and about Radar?
Yeah, happy to be on this podcast. So my name's Jeff, and I'm a principal engineer at Radar Labs. We are an enterprise geolocation tech company. So that's, a variety of things, spanning from maps and routing to search and geocoding and geofencing, as well as fraud detection. And a bit more about myself, I've been programming for quite some time now. I've worked at a variety of different startups. I've been a freelancer before as well, and even started my own small indie company a while ago. But these days, most of my engineering focus, I would say, is largely on backend and data infrastructure engineering.
What's your programming background? What other languages do you know besides Rust?
Yeah, so I would say, actually, it's kind of funny. When I first graduated from university, I joined a company called Foursquare. And I think at that time, it was maybe around the 2010s, where there were a lot of companies that were moving from Ruby, because Ruby on Rails, I think at the time was like, and it still is, but I think like it was almost like peak Ruby on Rails. And then there was the peak migrating from Ruby on Rails to something more quote unquote scalable, like companies like Twitter and like Foursquare and like SoundCloud. So it's funny because I worked at two of those companies. And so I've done a lot of work in Scala. In university, I prototyped and I was doing freelancing, and then I used a lot of Ruby on Rails at that time. And so, there are a lot of like web technologies involved with that as well. So I did a lot of JavaScript. And even at that time, there wasn't TypeScript, but I think people were using CoffeeScript at that time. So I played around with that quite a bit. It's funny, we migrated when I worked at PagerDuty. We moved some workloads from JavaScript to actually CoffeeScript, but I think it's pretty much defunct now. Nobody really uses it. So those are probably my main languages. Dabbled in Python and some C and C++, but never in like a really full-time sort of manner. And so these days at Radar, mostly working with TypeScript, some Scala for some Spark pipelines, of course, a lot of Rust, and yeah, what else? Maybe some Python as well. That's a matter in the base.
That's pretty impressive. Ruby, Scala, JavaScript, CoffeeScript, Python, TypeScript, that's a lot. And now Rust. What could people learn from the philosophy of Ruby?
I think this is sort of like an interesting question, because technology comes in cycles, I would say. And that's definitely something I learned with some of the like more senior like principal engineers at companies I've worked at before, where like really having an understanding and appreciation of things that are old really gives you insight onto like what's coming next, because technology really is cyclical. So I think there's a lot to learn and like about Ruby. And usually I would say the entry point for most people with Ruby is really Rails. So it's really that concept of making programming languages work for you, in some sense. And so what does that entail? It's almost like, especially in modern languages, a lot of us have come to really, be spoiled with these concepts of like very powerful list collections that you see from like functional languages. So like mapping and filtering and reducing, and even these concepts you can see are applied to like things that aren't even just programming languages, even in like distributed computation frameworks. Like literally MapReduce is that concept, and you see that in Spark, and with all the new sort of data infrastructure that's written in Rust, or even like SQL, because if you think about like the where clause in SQL is like a filter, or you can do reductions with grouping. Like they're all sort of these ways to express how you process data in a way that's like very elegant, and like it's commonly used throughout all these different paradigms. So I really think that, on the Ruby side, for me, when I first started, I was like, wow, this is like Python but better. But that's gonna make some people angry, obviously. And like that was me, being a naive like college student, looking at languages and seeing like, oh, where's the sort of trend going, and why is everybody using Ruby on Rails? And it's really just understanding that like it's a very pleasant experience and very expressive language, and having all of those like sort of batteries built in gives you a lot of productivity, and almost like brings more joy to programming, for really expressing like your ideas. Because really, at the end of the day, programming is about creating things, and it's almost like a creative profession that I think most people don't really assume is creative from the outside. But you're trying to solve problems and build things, and being able to express things in a very, I guess, like terse manner is very conducive to you sort of getting into the flow state as a programmer.
Yeah, when I think of Ruby, I think of elegance, I think of the joy of programming, expressiveness. Where would you see yourself more on the programming is a craft, or an art, or would it be more like discipline of engineering? Where would you see yourself on that scale?
I think it's a mix of the two things. You have the tools, but it shouldn't necessarily be like, the tools help you express something. So maybe like as like drawing parallels to maybe some other hobbies I have, like say you're a musician, right? And especially like in jazz music, like jazz musicians spend a lot of time practicing because they want to express like, oh, I want to play the chord changes in a certain way, and then like work on that, or I want to learn these certain scales. And at the end of the day, music isn't about scales or chords, but those are the tools you use to express yourself. And once you sort of have those tools ingrained, then they get out of the way, they come natural to you. Then you can express, your music, how you write music and add these things. So it's sort of like a mix of the two things, right? You want to understand the tools and what's out there, and they should help you really ship the thing you're trying to do. And the thing you're trying to do can be very technical. So in a lot of cases, you can get really down, like deep into the foundation, depending on what you're doing. A lot of systems programming, and this is a Rust podcast, right? So there's that side of things. But on the other hand, there's a whole, you know, ecosystem of digital products that don't necessarily need, you know, the best tooling or anything like that. I think, back to when, in college, like I remember just creating some small websites by uploading things to like an FTP server from some of these like, hosting companies that just give you a box and it's like, here you go, upload like index.php, and then wow, suddenly you have something that's connected to the internet. Like it can be something as simple as that. So I can see the appreciation for tools, but I really don't think it's necessarily going to. I don't think it's necessarily productive to just focus on it. But it's a mix. It's a mix of these things.
Coming back to Rust, with your background, Ruby, Scala, and so on, you have functional part down, you have the expressiveness down. That part must have been really easy for you to learn. Algebraic data types do exist in Scala, and now you come to Rust. How was that first impression to you?
Yeah, it was very refreshing. Rust really feels modern. There are so many things to like coming from, I guess, at Radar. Our main programming language is TypeScript. We actually migrated to TypeScript from JavaScript a couple years ago, but looking at the JavaScript ecosystem, where essentially there's a library for everything. There's a joke even on like Stack Overflow. It's like, how do you add 2 + 2? Just add this npm package to add two numbers. So there's having really even at the time where we first started building this, and we're definitely not early adopters. Like we started building our Rust project maybe 2.5 years ago or so. There's a rich like cargo crate ecosystem. There's a formatter, flame graphs, and the paradigms are very like functional, but you're not forced to use those either. So having, a rich like data structure ecosystem in the standard library, being able to process vectors with all of the sort of functions that many developers are used to these days really felt refreshing. And when we were starting to build out, HorizonDB, our Rust geo service, those were some of the characteristics we were really looking for, especially for a team with like largely a background in writing, TypeScript.
If you want to learn Rust on a deeper level and really get your hands dirty with challenging problems while having fun and seeing your progress at the same time, I recommend checking out CodeCrafters. I personally use it often to sharpen my skills and would recommend it to anyone who wants to become a better software engineer with Rust, or any other language for that matter. The challenges range from building your own shell to implementing Redis and SQLite, all the way to Kafka and DNS. This is perfect hands-on experience for backend engineers and systems programmers. And if you go to corrode.dev/codecrafters, you can try CodeCrafters for free today and get 40% off when you upgrade to a paid plan. Head over to corrode.dev/codecrafters or click on the link in the show notes to get started today. Mm-hmm. Take us back to that time. What was the tech stack like before you started HorizonDB? What was the team like, the team dynamics? I guess most of them would be TypeScript developers, but there might be other people in the team.
I guess like at that time, there maybe to give some background on maybe like the business side of things, we're sort of tasked to build essentially an address validation API. And so that's slightly different from geocoding. And we can talk about these two things. So geocoding, or generally it's synonymous with forward geocoding. That's what most people assume what geocoding is essentially searching for any geo entity, whether that's an address, that can be a place or a region. So those tend to be, more specifically called as like a coarse geocode. So for an address code, say I live at, 123 Broadway. The task is then to understand this query to know that this is an address and you're looking for the number 123 and the street Broadway, and then return a latitude and longitude. And with our APIs, we offer like some other metadata such as, oh, this is in New York in this postal code and things like that. And so for address validation, there's a slight difference. Address validation is more about understanding the deliverability of mail rather than being focused on, here's the latitude and longitude. It's more like, does this address exist in the post office's database? And so for us to accomplish that, the data format that we got from the post office, essentially they give you ranges of addresses. So Broadway goes from, let's say, 1 to 100, and it has this postal code. Or, 841 Broadway has, floor 1 to floor 12, and they have these specific postal codes. And it gets even more pedantic with the post office, and the rabbit hole goes very deep with address validation. So at that time, we were using an open source service for geocoding, but there wasn't really a way for us to essentially ingest these ranges and validate addresses. So that was sort of the main motivation for us to come up with something new. And so our tech stack, at that time didn't have any Rust. We have some front end, services written with React and Next and JavaScript. And then our API server was written in TypeScript. we had some like data processing jobs in Spark and Scala, and then we use Airflow, so some Python as well, but nothing really, statically compiled or, I mean, there's TypeScript, but more in the sense of like, these things translate into some bytecode, sort of like a JVM or into native instructions. And we were sort of expecting we had more constraints about like, oh, we're if we want to build a service that does things like this and it overlaps so much with geocoding, we might as well just sort of replace the service because we had some operational issues with our existing geocoder, which we can talk about later. And so there was sort of a motivation to use something that, whether it's like an external service like something like Elasticsearch, or having something like all in one. Operationally, this like we sort of got burnt by like having so many like external services that we were almost sort of motivated to have something that would just let us do everything on almost one package almost.
Was Rust the only language that you considered for that project?
So we were considering a couple of different options, and it's funny because at our company we write like tech specs or essentially design documents before we sort of go into building some larger projects or like features or things that will have like big downstream impacts. So like actually looking at back at the doc, we were considering a couple of languages. So and we sort of discussed the trade-offs there. So we were thinking about Kotlin, and the thinking around there is that the Java and JVM ecosystem is very rich. From my personal experience, I think Scala is very complicated. And, onboarding the whole team to that might have been a little tricky, but Kotlin is a little bit more closer to like, it's sort of in between. And I do feel like there's a little bit more of a backing around it now in the 2020s versus Scala. Scala really just seems like a little bit more niche in like sort of Spark. And even then, like, I think with Spark, I have some opinions about that and like how Rust might play into a world like that. So Kotlin felt like a good in between, and there's just a whole ton of these sort of interesting ecosystem aspects, such as Elasticsearch is written in Java, and essentially Elasticsearch is just a distributed wrapper around Lucene. I mean, obviously, it's much more than that, entire company. So it's a very broad stroke, but there's a whole ton of work around like text processing, which is essentially a
Right.
lot of this. And we felt like, okay, that is a very rich ecosystem that we could potentially use, with the trade-off of, we know we're probably going to have to store large text indexes and all of these things, like even like synonyms and or like different spellings or spell correction. Like a lot of this is like dictionary lookups of strings and things like that. So you can imagine, like, even from the onset, we're probably going to store giant hash maps or a lot of things in memory, and we'll have to deal with like a garbage collector. And one of sort of the motivating factors, from something like that as well, I guess before I talk about that, we were also considering Golang,
Hmm.
which, it's sort of similar boat, like it's garbage collected. So, and we've seen that a lot of companies have adopted it because it's really trivial to write web services, and it's relatively simple, in the sense that there's not a whole lot of different ways to do something versus something like a Scala. You can express like your problem, like how to do it in many ways. So those were sort of the two biggest contenders. And that was largely because we didn't feel too comfortable of transitioning, some JavaScript developers to something like C or C++. And I think the hurdle around like setting up like C and C++ projects, I know there's been so much innovation around, especially C++, but it just didn't seem like such a natural transition for our developers. And sort of similar with Golang, like I think Golang was sort of evolved from Google, from like their large C++ mono repo. And so like a lot of these like, things that I mentioned about like that make programming enjoyable is, things like mapping and filtering and like all of these sort of expressive aspects. We felt like because we had a bit of a short timeline, it almost felt like a step back in terms of like the sort of the joy of programming, or like being able to express, especially concepts where you have to like process strings like in very precise ways. Like in a lot of ways, a lot of searches is, if you ever do these like leak code problems, there's so much like string processing, and having more expression really helps you to make the code very clear about some very potentially like complicated ways that you process strings.
Which leaves us with Kotlin versus Rust.
Right. And so we saw like there was this, I think there's a very famous blog post. If you go on Hacker News and look up like Rust or migrating to Rust, I think the first result is always this one about Discord moving from Golang to Rust.
Yeah.
And so it almost sort of motivated us to see like, oh, they had occasional garbage collecting issues. And even working at like other companies where we use Scala and the JVM, like there was consistently like issues with like the JVM and like the garbage collector. And there's so much innovation around the garbage collector, but we knew like for a lot of what we were doing, text processing and indexing, things like that, we're going to store large data structures just in memory. I know there's like these concepts of like off heap memory, but that's already sort of off the happy path of the language we're using. So we're almost like putting a barrier or like something impeding us before we even got started. So we really did want to have something where we had a lot more control over the memory. But we also didn't want a language like C or C++ where you sort of have to expect developers to understand these like concepts. Like they still need to understand these concepts to some extent, but you have to be really, really upfront and like be very almost very, very strict about these things. So that would require significant like senior engineering talent within that had like C and C++ knowledge, which we didn't have.
Mm-hmm. There's a lot of ceremony around allocating and deallocating memory in C. Not so much in C++ nowadays, but definitely in C still. And when you say garbage collectors, yeah, that is also true for both Go and Kotlin or Java to a wider extent. I remember that in the past we ran a very large Elasticsearch cluster, and those were different times. We tried to migrate that to containers, and it wasn't really easy because operationally Java had some unfortunate default decisions where it would try to allocate as much memory as it could possibly get on the machine. And if it's co-hosted with a lot of other services on the same machine, that sometimes caused some problems. So did you also run into, or did you also consider these kind of concerns, the operational part of it, the deployment process?
I guess specifically for, how you mentioned Elasticsearch, actually one of the things that, also sort of bit us and also why we decided not to use a JVM language was the fact that we did have to maintain an Elasticsearch cluster to power geocoding with our old iteration of the geocoder. And we realized we just had to put everything on one machine, which is still the case, but we didn't even use really the sort of distributed aspect of Elasticsearch because of the nature of the workload. It would just end up, essentially fanning out all the queries to all the nodes, even though they're sharded. So at that point, we just essentially just got one really like fat box, and all the shards of the Elasticsearch cluster just lived on one box. So it almost defeated the purpose of that. And so, maybe this is more of a design thing more so than Rust, but, that motivation of, Elasticsearch was, contains, let's say, a bunch of geodata and like addresses and places and things like that. And there were a couple of other microservices that we had powering our old geocoder. What we really wanted was not just like a deployment story that was simple for essentially the binary, but our data assets as well. And so what that meant was that it would be much simpler where the old world is essentially, oh, hey, I want to do a migration. And, developers deal with this all the time. If you want to do a database migration, you essentially have to reason about what's the existing state of your database. If I want to introduce a column, can my or you got to make sure that maybe everything can handle null to begin with. And then, maybe you have like a state change. Maybe you want to increment something. So you have to, understand that the state of your database looks like this. You're going to apply this operation. What happens if your database script fails? Then, you got to code in this concept of idempotency, where you can rerun the script many times. And that's a lot of things to reason about. So, in terms of a deployment story, for sure, we wanted something that was very simple to deploy, and Rust just gives you a simple binary. And, we essentially compile it in CI and essentially ship up the binary to our servers. But also the data assets, we wanted it all to be, self-contained within the same server. And even the way that we process it, actually, we rebuild the data sets from scratch. We never backfill anything. We just take all the raw sources and then, distribute the compute with something like Spark and essentially compile it to, some data assets. And there are some things that are more specific to, the data formats that we use on our server. So we process those later. And then we ship those data assets to all of these boxes. And so, what that means is because everything is self-contained, it's actually very trivial to roll back, which is something that you might not be able to do if you had, say, like a third, like if you very simple, like two-tier architecture, even a web app and a, say, SQL server. If you do a data migration, that you have to reason about the data migration roll back and forward, as well as the binary data roll back and forward. But with our new service, it all sort of goes in one package in lockstep. So if you need to roll back, you just switch everything over and all the data pointers also switch back. And so that's a way to roll back. And you don't have to reason about these many states. It's just one self-contained thing. And for that to work, you really do need something that's like very efficient, essentially, both in because you're shipping such, so many data assets. And
I see. That's an aspect that I never heard before. Because Rust is so fast, you can afford to simplify operations by doing more at startup, but it's still performance. So you can cut some corners thanks to Rust.
Right, because it's almost like, hey, you don't even need an external database for something like you would typically grab for in web apps like a Postgres or, MySQL. It's, hey, I'm going to use an embedded database or have a large in-memory index. And that's your sort of state. And so all of that ships together in one whole, unit or package.
What do you use for the storage layer?
So we use a couple of things. And so we talk about this in, the blog post that describes HorizonDB.
And we link to it in the show notes. It's a really, really nice write-up.
Yeah. I would say our primary storage mechanism is this thing called RocksDB, which is a embedded storage or embedded database. And the way people think about it is it's essentially the database that you use to build databases. So, for example, Facebook or Meta, they originally used this to power the storage layer of MySQL for them. And I think there's a project called MyRocks. MongoDB, for example, they actually use RocksDB for some time. If you look at CockroachDB, their storage layer for a long time was also RocksDB.
Same for InfluxDB.
Right. There's so many projects around there. And so much community backing that we felt it was such a mature project that we could use it for our purposes. I know for sure there are a lot of like Rust crates now, things like I believe Sled, stuff like that. There's many people who write, these sort of embedded databases. And essentially RocksDB is this data structure called a log structure merge tree. And it's really designed for high write throughput, which is sort of different from our use case. But like I mentioned before, technology is so cyclical where, if somebody builds a database that's like high write throughput, well, they actually adopt a lot of these concepts and ways to tune it so that, it's also very well tuned for read throughputs. And so we just felt that, that, community backing and the sort of, and it's a project that's written not in Rust. right? So that was a sort of another nice thing. We had all the Rust bindings to RocksDB, and it was very simple like integration to be able to just pull in that project. And that is our sort of primary storage layer for, all of our entities. So addresses, places, and different regions. And so it serves, a number of different purposes. So obviously like primary key fetches. So when our services have, say, like an event and they have an ID for a place, they'll fetch, that from our service. But we also index it in a way that makes it really easy to do geo lookups. So given this lat long, I want to be able to fetch all the relevant geo entities. So am I inside the city? Am I inside this country? Things like that.
RocksDB is very fast and very write focused, but also it's effective in terms of storage. And I guess that plays in your favor, because if you try to geocode the world, you need a lot of storage. And on top of it, once the storage is quite optimized, you get really decent cache locality on top of it for free.
Right.
So it might have been a really great choice.
Yeah, there are a lot of nice aspects about a log structure merge tree. And I think most like modern database implementations use that in some shape or another. And it's largely this concept of, obviously there's so much engineering around it, but like everything is sorted. So that gives you a huge advantage, and like that is something that many people take advantage of. So in our blog post, we talk about, very fast geo lookups using this library called S2, which is essentially a geohashing library. And so what that means is you have a latitude and you have a longitude. That's 2 dimensions, right? And so it's not clear at first how you can use sorting to help you make lookups faster. And so I mean, there is literally a thing called geohashing, and there are other like implementations, such as from Uber, there's this thing called H3. From Google, there's this thing called S2. And essentially it collapses, the latitude and longitude into a single 64 bit, or a U64, I guess, in Rust terms. And it has many nice properties because it tends to be the case. Obviously, there's boundary conditions because, latitude and longitude, and they go from negative 180 to 180 and negative 90 to 90. So there are some boundary conditions to take into account. But for the most part, you maintain, because of like, somebody who's smarter than me who came up with this thing called like using a Hilbert curve, you have a locality with adjacent IDs, which means that things that are close to each other will be, if you sort it, will be next to each other. Obviously, barring some boundary conditions, but that fits really well into a system that has, things sorted like a log structure merge tree. So you're able to make very efficient range and geo queries from something like that.
Mm-hmm. And all of that combines into a very efficient single binary lookup service. What do you use for the fuzzy searching part that you mentioned?
Right. So this is more related to the forward geocoding side, which is, essentially translating your text query into some sort of, geo entity.
Mm-hmm.
And so one of the requirements we had to deal with was essentially being able to handle a little bit of typo tolerance from our address validation service. And that comes in many different forms. Like there's so many like sort of failure cases for search, which is a little bit different from like more typical web applications. It's like you click through a couple things and that you expected this. Really, like all the different use cases are literally every type of single character that a user can type. Those are all the potential use cases. So the cardinality is extremely high, and essentially the number of failure cases is almost unbounded in some sense. There's just so many combinations that at that point, like there's so many ways to type something in. So we deal with fuzzy search in a couple of ways. We use a library called FST, and I remember there's an episode you had with Charlie Marsh from UV, and I think there's an engineer who works there now. I only remember his GitHub name because it's very memorable, like Burnt Sushi. But he works at UV, if I remember correctly, and he's come up with a lot of really interesting Rust crates. And I think he even implemented the regex or did the regex implementation of Rust. So
Yeah, exactly. Jonathan Gallant. Yeah.
right. And yeah, so we make a lot of use of his libraries, but FST is essentially a character graph. And so there's this concept of like a trie that's very typically used for prefix queries. And so you can sort of think of an FST as like a trie where, all the prefixes that are shared compress, but it also compresses the suffixes. So now you have almost like double compression, right?
Mhm.
And essentially doing text lookups is a traversal of the graph. And you can see how that sort of primitive lets you do many things. It lets you implement like a regex because the regex sort of works the same way. And so for fuzzy search, you can implement like Levenstein distance by essentially keeping a way of dropping, or like if you type something incorrectly, you can have like certain thresholds that we use like an edit distance of 1 because more than that it's essentially combinatorially expensive, and we have other techniques for typo tolerance, but we use this library essentially for one, obviously prefix search, but then two, it does have some built-in ways to do Levenstein distance, which we're actually starting to move off of a little bit because now we're actually, as the project is starting to succeed, we're getting more queries. And so because what users typed and what their end result actually was, we're able to, at scale sort of figure out, oh, these typos actually map to this type of this actual correct spelling. And so we're able just to do those lookup much quicker. But the funny part is for some of these cases, we actually also index that into the FST. So in a lot of ways, the FST is almost like a cache. You can almost think of it as like a hash map or maybe even a B tree map of a string to a U64. Like that's how you would it's maybe a compressed version of that. But it's even more than that. It's really just like a way to cache high cardinality text in a very
Mhm.
compressed way.
Yeah. The way I always think of an FST, and I might be wrong here, is it's a very fast state machine for looking up the existence of words very efficiently and very quickly. So you mentioned the trie data structure that is similar, where it stores all of the inputs in a tree, but it knows when there is no possible way for a word to exist in the data storage because you reached a leaf node in the tree and there are no child nodes. So, for example, this is not a hit in your data structure. And in your blog post, you mentioned a few other crates. We just wanted to quickly do a quick shout out here. 10TV would be one, LightGBM, and Fast Text. What are these?
Right. So I'll give a quick rundown of these. So for any sort of search system, the most fundamental data structure is this thing called an inverted index. So that implies like a forward index. So maybe I'll explain what that is first. And so like forward index is more like a traditional database. So record 1 maps to Broadway, record 2 maps to Prince Street. The inverted index sort of switches that around. So you first tokenize, and that is its own like whole topic. Like people research on how to tokenize text, especially with all like AI and machine learning trend now. But you can then say, oh, Broadway, the token maps to ID 1, and then Prince maps to document 2, and Street maps to document 2. So when you type in Prince, then it's not a hash map in these implementations, but essentially you just look up the word Prince, and then you get all the documents that are related. And so once you have these documents, you can sort of perform these set operations to essentially narrow down which documents are relevant. And then 10TV offers this thing called BM25, which you can think of it as like TF-IDF. But essentially, once you have these documents, and this is the difference between a database and a search engine, how do you essentially rank which of these documents is most relevant? And that is its own, that is its own like sort of. There's a lot of work around figuring out what is the most relevant. I mean, it's different for every company and every use case. So TANTB, that's a library that came from, I think, these people from France, and they were building essentially. It's funny, it's an Elasticsearch replacement, which is, we've been talking a little bit about that, called QuickWit. And so there's just a lot of primitives that that came along with this sort of Rust ecosystem, and that was one of the libraries that really drew us to using Rust. We're migrating to a different implementation that doesn't use any of these libraries now. We use this thing called Roaring Bitmap, but it's the same concept. And we're doing that largely because of sort of the more structured nature of some of the geoentities we have. We have addresses and regions, and people tend to type addresses in a certain way, so we can take more advantage of that and fine tune how we, do our search workloads. But at the core of it really is this concept of an inverted index. So that is, I would say, the core of geocoding. And then we can talk a little bit about light GBM and fast text. And these things always move very quickly. So we're actually considering moving off of these libraries, but we're still doing something that would serve what these libraries do. And so light GBM is a gradient boosted tree. I think if you take any basic machine learning courses, you'll learn about decision trees. So the concepts are really the same. And essentially, it's a way to do a couple of different functions. First is classification. So if I receive an email, does it seem like a positive sentiment or a negative sentiment or a neutral sentiment? It does interpolation. So given the name and the country and, I don't know, the sports that somebody does, try and guess their height. It's like, 4 feet to, I don't know, 7 feet, something like that. And that's interpolation. It does learn to rank, which is particularly interesting. And as I mentioned, we do, from the inverted index, we do ranking, which in some sense is like really just a primitive of classification. But essentially what it's saying is like, given this list of entities, which one has the highest rank and which one has the lowest rank? And you can really just think of that as like pairwise comparison. So like if I type in 841 Broadway and I'm in this latitude and longitude, is it referring to 841 Broadway in Brooklyn or 841 Broadway in Manhattan? And so that is essentially what learn to rank is, but you can apply it to more entities than just two. But really, it is just sort of classification if you think about it.
There's a Broadway in Brooklyn?
Yes, there is. I think when you start to learn about the world and like, I don't think people are really all that creative with naming things. And so it's not just programmers that have problems with naming things. It's everybody has those issues.
Nice. Well, it's just a wide way. It's just a wide street, so totally makes sense.
Right. It is also a very wide street in Brooklyn, so that's.
Yeah.
We consistently have issues with people trying to figure out which Broadway we're talking about.
Okay, we have all of those libraries. Just to recap that part, when the service boots up, it starts to ingest all of that data that is more or less stored in some flat storage. You start to ingest it. You start to build your, let's say, understanding your model of the world, like quite literally. So, and then you have that highly efficient lookup functionality. And through the API, then you can find addresses really quickly and map addresses to certain geolocations and maybe even vice versa if you needed to.
Right. Yeah, and you can already see that like because there are so many of these assets, the startup time does take a little bit of a hit.
Can you roughly tell us how long it takes?
So we download all these assets in parallel from S3, and we do actually try and sort of cache these assets. So we deploy in Kubernetes, and generally when we're making new releases, only a couple of things change. Like, oh, maybe you only updated places, so we only need to pull those changes from S3. And so it's maybe like a couple minutes, But really, like the future of this is we want to get it to, less than a minute or even like in like 30 seconds or so. And so this is another area where I think Rust and like having and like all the work around the data infrastructure area where like a lot of like before it was like a lot of these Java services from all the Apache projects, they're all using Java. We're seeing like a whole ecosystem of these data infrastructure pieces being moved to Rust or like, and so one of those things is we do want to start to separate the storage and compute in a way that our database can start to come up right away or download the minimum amount of assets. And the fact that we almost like memory map some of these like assets, you can actually translate, that in a pretty straightforward way with S3 because it offers like a range API. And because like people have built libraries to essentially cache S3 on disk, what we're thinking about is we're going to build a storage layer that almost caches S3. And then while the service is booting up and hasn't pulled in the assets to the local NVMe disk, it can temporarily sort of pull in ranges of bytes from these like storage services so it can immediately start serving queries. Obviously, there's going to be a latency hit, but in terms of being able to deal with things like, oh, we have a traffic spike, that's where like, that's sort of one of the problems we're trying to solve. And I think the fact that there's so much development around, data infrastructure projects, and, we use Spark at Radar, and like so many companies use Radar. Just this whole concept of like data infrastructure in the cloud and using object storage, like we're seeing like, new streaming frameworks written in Rust or a lot of these sort of new iceberg tools in Rust. And that's going to help us a lot for building something where we want to separate, or it's going to accelerate essentially like what we want to build where we separate storage and compute.
How long did it take you to build and ship the first version of HorizonDB?
Right. So as I mentioned before, like our first use case was address validation. We had a customer who was asking for it, and we built it in about a month. Actually, I think less than that, like to actually get something working. But to get it closer to like full production with this customer, maybe it was like 2 months. But it like with a lot of QA and like a lot of feedback, things like that. But I would say it took about like 2 months.
Did you have a lot of outages due to Rust? Production outages?
Not really. One was because we were only onboarding a single customer and like the QPS wasn't like that high to begin with. And two, because we had this property of everything was sort of self-contained, it was very trivial for us to do blue-green deploys, which also includes the data as well. So like, hey, you process the string in a wrong way and you're starting to see that, you just flip it back to the previous service and it's all self-contained. Whereas that might be harder to do with like a single like backing database or things like that.
Can you even remember a single outage or a single error or a panic in production with Rust?
Yes. So I will say we do make use of this geo library from Rust, which is very popular. And one of the top issues is that it panics and doesn't handle errors, which is like un-Rust-like, I guess. We have this service called Sentry that we use for error logging, and there's essentially no like exceptions normally apart from like that library, but typically we don't see stack traces. We do see outages, and that's just due to like spikes or like essentially queries of death. And there, we can, there's a whole podcast to talk about like reliability and things like that. But the service itself is pretty efficient, and our rewrite of the search indexes is going to make the service even faster. And as I mentioned with like the storage and compute separation, that's going to introduce like another level of scalability and like being able to handle like spikes in a way that, generally I would say like if we're looking at the proportion, and really there's two main backend services. There's our API server and then, HorizonDB. I would say there are not like significant amount of outages from that.
And talking about scale, can you give us a few numbers? Number of requests, number of nodes, etc.
Right. So at a steady state, we're looking at about 18,000 queries per second.
That's a
The
lot of
workload.
queries.
Yeah, I would say it's a lot. Maybe it's like at other companies, it's not like super high in some, like, because like there are some cases where like things will fan out and then suddenly you get like hundreds of thousands of TPS. But yeah, it's enough to know that like if you made like a certain optimization, like you can quickly tell if things went right or went horribly wrong.
How many nodes do you need to handle that traffic?
Right. So we have 30 nodes. It's significantly over provision now, which is why we're looking into like how we can, be more efficient about dealing with spikes. We already actually shard out like the database servers by like different use cases and by different like tiers of customers because we are a SaaS company, just to reduce or essentially just to isolate certain workloads and prevent like outages from bad query from one customer affecting others. So we all that's to say is like we are quite over provisioned there, but we're working on it.
Well, it's great. You could do with less. That's
Right,
that's always a good thing that
right.
managers want to hear, because saving costs becomes much easier if you can just shut down some of those nodes if you don't need them at the moment.
Yeah, that's right. Cost cutting is like I wouldn't say it was the primary thing for getting this started, but we did see a lot of benefit from that. So even running 30 nodes, we're able to replace, a number of like Elasticsearch instances. And we represented like geoqueries in many different ways, like denormalized across different stores like Redis and Mongo as well. And then in total, I would say actually, even with the 30 nodes, and the over provisioning, like we probably saved, maybe mid to high five-figure monthly spending for some of these things.
Impressive. How many queries per second does one box do, and how much CPU does it use roughly?
Right. So on average, which is a misleading metric because forward geocoding, which is search, is a very different workload from reverse geocoding. We do 600 queries per second per box, and
Hmm.
it's about 20 to 30% CPU at the steady state, which means it can go higher. And I would say that, our search workloads are probably like a 10x, sometimes even 100x of like reverse lookups as well as like primary key lookups.
Would you say it's a rather CPU or compute bound problem or a storage or IO bound problem? Because on one side you have hashing, which can be very expensive, but maybe that's just a thing that you do at the beginning when you boot up, and then it's not really as compute intense later on during operations. Or would you say, well, no, actually, that is kind of the bottleneck? Or would you say, no, the storage part is the bottleneck?
Right. So breaking it down into like the different use cases for geocoding, which is search query, reverse geocoding, which is like a lat long lookup, and then maybe even like primary key lookups. I would say the latter two are more IO bound. Maybe you pay some cost of serialization, deserialization from some of the storage systems, which will change soon because there's a lot of very nice like zero copy libraries from Rust. And so the CPU intensive queries tend to be of search. Yeah, I would say it's actually both because if you think about it, like as I mentioned, this inverted index structure, if you have to do many key lookups, right? You tokenize your query 123 Fake Street, Brooklyn, New York. And in fact, there's many ways to express it in synonyms. So maybe you expand the query and maybe instead of 123 Fake ST, it could be street. Or if you know the users in Germany is Strasse, and and we haven't indexed or normalized everything in a certain way. So we do expand the queries, and you can see how it can fan out to many keys being pulled back. And once you have all these candidates, you essentially have to rank them. And so there is a little bit of, CPU intensiveness in that, but we're working on optimizing these things. So, and I will say that if you do decide to build this sort of an analytics or search system, we're very big fans of this new approach with Roaring Bitmap, which is it's actually an implementation that you see across many different languages, but we found at least from the sort of candidate fetching where we're essentially in the inverted index and trying to pull out which candidates match a criteria, those tend to be like microsecond operations for most of our geocoding queries. So that's why we're sort of moving over to a more like dedicated and specific system for our use case.
Yeah. You said it yourself, lots of moving parts. What's the median latency of a forward geocoding request
Right.
and maybe a
So,
reverse geocoding request in comparison?
yeah. So the median latency is about 50 milliseconds. And that's because when we were building this system and we were seeing customer queries, we're seeing that most customers tend to enter the right thing more or less. Like they tend to enter their address correctly, even if there's like some spelling mistakes, but they tend to uh, have a more predictable sort of query pattern. And that's sort of why like I described the FST as like a high cardinality text cache, because almost everything, like I would say 70 to, it depends on like the what you're querying, but 70 to 80% of the queries, especially for US and Canada addresses, will just hit the FST. And all of that is we have the sort of generosity of being able to store all of that in memory because it's so compressed. And Rust, we're writing in a way that's a single process and multi-threading for concurrency versus something like Node, which concurrency, or like Python, where I mean there are starting to be thread concepts, but the classical way is just to have multiple processes, and then that means you need multiple copies of the data structure in memory. And so oftentimes we're hitting that, and those, at least that side of things, those operations are usually at most like single digit milliseconds. Depends on like the query, but a lot of times we will see things show up in less than a millisecond for that side of things. For reverse geocoding, as I mentioned, we sort of like to speed up your algorithms. Oftentimes it's like, can you sort it or can you hash it? And essentially, we have hashed it by taking the S2 library where we convert the latitude and longitude, 2 dimensions, into 1 dimension. And that's essentially just a key that you look up in RocksDB. So many of our workloads look like that. And once it's like that, it's almost no different from like a primary key lookup, right? It's just a key value lookup. So we're seeing less than a millisecond for those types of workloads.
Nice. And all of that with how many lines of Rust code in total for the server implementation at the moment?
Right. So in terms of our code base, it's about 150,000 lines, which I would say is actually not very much. And if I haven't taken the time to like analyze like which code line is serving which use case, but I will also say like there is like a good percentage of stuff that's like kind of hard coded right now that we could probably, I think, to get like a minimal implementation, maybe like you could, when we first started doing address validation, it was like a couple thousand lines. It wasn't anything too big. So, and that sort of speaks to like how expressive, being able to express certain concepts in Rust is.
Are there any tips and tricks that you could share with people who are planning to build a larger Rust application? I'm thinking of composition patterns, usage of traits, how you structure your data objects, immutability, anything that comes to mind that you learned maybe that is uncommon in Ruby or Scala or any other language that you knew before?
I would almost like take the approach of almost, especially when you're starting out, not to overthink these things. I do think that Rust still has like so many different concepts, and we're always like, honestly, as we're writing, we're not, I don't even feel like I'm an expert in Rust at all. Like I always learn something new. So with that in mind, especially like if you're first starting out with Rust, just try and get something to work and then sort of optimize after, because I guess they always say like premature optimization,
It's the
is
root
it
of all evil.
basically, yeah.
Yeah.
So try and get the simplest thing to work, and then you know, only apply design patterns if you're starting to find you're really repeating yourself or it becomes very finicky. I will say that, especially in this age of like AI editors that will essentially copy and paste everything for you, I don't know. But yeah, that's the way to think about it, is really just to, rather than take very like high level approaches where it can actually sort of inhibit or prevent you from being able to do the thing you wanted to do. Just do the simplest thing and then apply more optimizations or introduce more sort of design patterns as you start to see the problems arise. And like, then you really do get a sense of like what problem you're trying to solve.
Yeah, perfect. That's right down my alley, even in a geocoding sense, because I recently wrote an article called Be Simple, and I'm very much in favor of that. Unfortunately, we're getting close to the end. We had a blast, so the time flew by. The last question is, what's your message to the Rust community?
I would say, obviously, keep doing what you're doing. I think the Rust ecosystem is very vibrant. I think there's an interesting trend that I've seen where, and it's almost like Hacker News driven, where it's like, oh, I built this service and it's written in Rust. But we're actually even seeing in not even like a like we're seeing that is in almost like a marketing approach for real businesses. Like there are so many sort of new, like interesting pieces of infrastructure that are becoming businesses that are like open core, or I wouldn't say it's like fully open source, because I think the open source peers would be, it's like really depends on licenses. But I think it's such a flexible programming language, and it's very modern that you get a lot of these sort of productivity or enjoyment aspects that you would get from maybe some other like scripting languages traditionally, that I would love to see, more of these like businesses that are really like open source and open core to really inspire what you can really do with the language. And I would also love to just see more work around even just doing the sort of 80% of things that most developers are doing these days, which is really just having a nice like web app experience. I think there's still a lot to do there. I know people brand it as like an infrastructure or systems language, but it really is like a very enjoyable language to use for many different use cases. Even like I think, so not this instrument, but I know like Electron, they're in Sweden, and they make like a lot of music production equipment, and a lot of their code is written in Rust. So like you really see like all these like different aspects, because like it's a language that's very expressive, but on the other hand, it lets you get really deep in the weeds. And so it lets you do so many things. So I would love to see like more, support and work around even just like basic things like a lot of like web apps. Like who knows, maybe there will be like a Rails for Rust in the future. That would be super interesting.
There's LocoRS.
Yeah, I guess that's true.
Jeff, that was amazing. Thanks so much for taking the time today.
Yeah, likewise. It was a very fun chat.
Rust in Production is a podcast by Corrode. It is hosted by me, Matthias Endler, and produced by Simon Brüggen. For show notes, transcripts, and to learn more about how we can help your company make the most of Rust, visit corrode.dev. Thanks for listening to Rust in Production.